Well, we had a look at the Kurzsignale CW message, the compressed message, very short, designed to avoid detection by the Allied DF systems. Unfortunately for the U-boat captains, those transmissions were long enough to be detected and to be DF'd, and a lot of useful information was obtained from those signals. So the Kriegsmarine, which is the German Navy, set to work to devise a new system which would be much harder for the Allies to detect and direction find. And the system that they came up with was Kurier. And what we'll do now is have a look at a typical Kurier system, just to understand how it worked and why it made detection so difficult. So what we have on screen here is part of the Kurier message. Every Kurier transmission, and there was only one transmission made, this was not repeated, unless conditions were particularly bad, but normally only one transmission was made on a given frequency. So the start of the transmission, you'll see there are many dits that are sent, so there are 25 dits sent. And then there's a quiet period, and this quiet period is fixed, and the number of dits is fixed. And following the quiet period, we have the actual data itself. And the data is again sent in CW, in Morse, but the build-up of the Morse characters is different to conventional Morse. Instead of having 3 dits to create a dar or a dash, the Kurier system uses 2 dits very close together. So this is a dar. So we have dar, dit, dit, dit. So dar, dit, dit, dit is letter B. This is what a letter B looks like in the Kurier system. So if we move on to the next character that was sent, this is also dar, dit, 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 so it's another B. And then the next character, we have didar, dit. So that's an R. And between each letter, there's a slightly longer gap. So you'll see between this B and this B, there's a gap here that's just ever so slightly longer than the inter-character gap. And between this B and the R, there's a gap that's just a bit longer. And then the next character we have after the R is dar did it, which is a D. And this is how the message is made up. Now this message here is exactly the same as the Kurzsignale Morse message that we heard earlier. Exactly the same message. So the same Morse characters, but the Morse characters are constructed differently. They don't have the same wave form. So what we'll do, we'll have a quick listen to the Kurier system and see if you can see why the Kurier system was more difficult to DF than the Kurzsignale. So let's switch on the speaker and we'll listen to this transmission. That was a transmission. Did you catch it? So as you can hear, it's very short. So the Kurzsignale is extremely short, and it only lasts for less than half a second. And it relies on a number of strategies to avoid detection. First of all, it is transmitted on a different frequency each time. So the U-boat and the ground stations have a table, a frequency table, which defines the sequence of frequencies that they'll use. The message is also encoded multiple times in the same way as the Kurzsignale message was encoded. And in addition to that, the transmission is sent once only, as I mentioned. Now, you might wonder, how does a receiving station decode such a fast signal? Obviously, being Morse, it's decodable, but I defy anybody to decode that brief transmission. Let's just listen to it once more. There, you couldn't possibly decode that by ear. So here's how it worked. Let's just grab a transmission. just capture one. Right, there we go. So what I'm going to do here is just have a close look. So we have our 20 characters or 20 pulses followed by a space followed by the data. So the receivers consisted of 3 Philips R101 receivers. We've got a photo of that on the screen. And the output of the Philips receivers, the speaker output, was sent to a full wave rectifier. And the full wave rectifier produced a waveform very similar to what we see here. So for a good signal, a good strength signal, you'll have something like this being rectified if you looked at it on an oscilloscope. And that's exactly what they did. They used the 20 pulse preamble as a trigger for the receiver. So the receiver was sat on the frequency, and as soon as the transmission occurred, these 20 pulses would tell the receiver that a message was about to follow. So we got the 20 pulses, a wait period, and during this wait period, what happened was an oscilloscope was triggered. It was enabled, so it was on standby. The filament was hot at all times, but it was triggered, and the oscilloscope would capture the waveform coming from the receiver after rectification. And at the very end of the signal, once the signal had ended, a trigger was sent to a solenoid, and that solenoid triggered the camera that was looking at the oscilloscope. So the oscilloscope had medium persistence phosphor, and at the end of the message, the camera took a photo, and the photo would look exactly the same as we have here. And that photo would then be developed and sent to the signals department of the Navy. And what they would do, they would put that under a magnifier, and they'd zoom in on the characters, just like this, and they'd go from character to character, and they would write down the characters that were sent. Then they'd put those through an Enigma machine to de-enigmarify the message. They would then put the decoded message through a number of backwards tables to extract the original message. And that was the way the system was designed to work. So it was very rapid, very effective. And if the system had been in place early in the war, it's almost certain that the Allies would not have been able to make such advances in the breaking of the Enigma code and the various table codes, because the chances of detecting the signal would be so much less. It really is a very clever system for compressing a lot of data into a very short space of time. So for the 1940s, this was quite remarkable. However, this system had its problems. The way that the system created the message was very manual. The operators would get the starting message, so it would be something to do with the weather or bearing or location, and they'd encode that using the lookup tables. They would then convert that through Enigma to get a secure version of it. And then once they've got the secure version, they would actually program these individual pulses, and you'll see that every pulse is exactly the same length. There's no differential between a dit and a dar. Everything is an equal pulse width. It's just the position of the pulses that determines the actual code. And they'd actually program this message onto a rotating disc. So each pulse would be defined by a small iron blob that would be placed on an aluminium disc. And that disc, once it was completely filled with these blobs, that would be sent to rotate on a synchronous motor. And that synchronous motor, there would be a coil that would detect the iron blobs going by, and that would be amplified and squared and act as the modulation for the transmitter. The system was unfortunately riddled, well, fortunately for us, but unfortunately for the Germans, riddled with various challenges. Temperature and humidity changes would make the the system fail. It was not very reliable, and ultimately it was not used in the war, much to our benefit. So this is the one of the reasons why DF systems such as the elephant cage were very important, because had this system actually been deployed, the elephant cage would have been an ideal candidate for detecting and also deriving the bearing. So a number of elephant cage systems around the world would have been quite successful in finding the bearings of such a transmission. However, had that happened at the beginning of the war, there's every chance that the detection would have been very unlikely with the technology that was available to the Allies during the war. So that's the Kurier system.